Hello, hello. It's probably time to start. I guess some people might be late, but we don't want to keep you waiting. We'll speak in English anyway, even if everyone here speaks Polish, because this is recorded and will be published. So, welcome everyone. Today we'll talk about Google Cloud Platform. This is the second in the series of 4 talks about Google Cloud Platform. Today we'll focus on the compute part, and we'll do this together with Michał Kotnowski, who is our one of the major partners for Google Cloud in Poland, working at Go Cloud.pl and helping Polish companies to move to cloud.
Good afternoon, everyone.
We'll also have Thorsten, who will join us later and help answer the questions. He's the customer engineer lead for the CE region. And my name is Jarek. I'm the engineering manager working at Google, working on the data center infrastructure, software infrastructure, and the cloud infrastructure. So today we'll briefly talk about how Google thinks about cloud, but very quickly, and briefly talk about the data storage and data processing solutions. But around 97% of the time we'll hopefully focus on the compute options. And I will tell later what it means. So this is a short repetition of what we actually said on the previous. By the way, how many of you have been on the previous instance of this series? Raise your hand. Okay, 4 people. Okay, so I will probably not assume this knowledge. Still, this will be just a short introduction. So the way we think about cloud, about the whole transition is the following. So the way people have run their companies, their IT part of the business 10 and 15 years ago, and still majority of people, I think, in Poland do, is they have a physical set of machines, physical data center, or they use some colo provider or rent some machine somewhere, but basically they get the physical machines, they buy them or they rent them, and they run software there. And that has worked for many years. But over time, people realized that this is actually this means that they have to do a lot of stuff that others also do related to management of this hardware, ordering those machines, fixing them, making sure that they have a good backup disaster recovery methods, etc., etc. And also what's also important is that it was a very time-consuming effort to actually get more machines. Like if you need a few more machines, it takes a few days to order them, right? So people started the move, and I think this move more or less started around 5 years ago, or maybe the beginning was maybe 10 years ago, but really it was noticeable 5 years ago, and people started to move to public clouds. So what it means that instead of having a physical machine in their data center, people go to public cloud and say, I want to rent a virtual machine. They get a virtual machine and they can get it for half an hour, for 2 hours, for 5 hours, and they pay only for this period, right? And they don't care what happens when the machine breaks. It's not their machine, they will get another one. That's not their problem. So basically, you don't have to care anymore about managing the physical hardware. And it's particularly important for startups, which I think is majority here in the room, because in case of startup, you have a new idea, you might want to try it, you might need a lot of machines for a short period of time, but then you don't care after that, right? Or you might change your plans. And so that allows you to very quickly test something, test the idea, very quickly go to the market, and then if it's successful, great. If it's not successful, you can very quickly stop, and you have not invested any capital in the machines. So you don't have to worry about the hardware. However, inside this hardware, you run software, right? And in this regard, really nothing has changed with the move to public cloud, because you still, when you move to IaaS provider, when you run virtual machines, you still have to manage everything that's running inside virtual machine. You have to write the code, you have to manage the operating system, you have to watch out for new security vulnerabilities that has been discovered, apply security patches very quickly, etc. So the next phase of the move that we see here and we also participate in is move to the platform as a service solutions or no-ops solutions, where actually not only get rid of or relieve you from managing the hardware, but also relieve you from managing some of the parts of the software running on the machine. And there are different flavors of that we'll talk about later on. So what is Google offering in this space in particular? So Google Cloud Platform actually is 3 components. So first of all, we are offering basic cloud infrastructure. If you want, you can get the middle part from the previous picture, and there are cases when people really need it. And Michał will give a demo explaining what are those cases, so you can make the informed decision. Then there are platform as a service solutions, which allows users to leverage write code, but write code in a way that only focuses on the business part of the application and of your application, and the rest is managed by the system. And there are software as a service solutions, so you actually don't write any code. You just use a service running in cloud, and great examples of that are big data tools. Like you just upload your data to the cloud, and you run some data processing on it, and you get the result. And you temporarily use some of the machine power that's there in the cloud. You use number of machines, but maybe only for 1,000 machines for 10 seconds. And your data analysis is complete, and you are done. And you don't need those machines anymore. And what's specific about Google is that Google has been building this type of a cloud for itself, for its needs, for around 19 years, I think, now. And when we entered the cloud business, so by entering cloud business, we mean public cloud, so started selling this to other customers, we actually started basically taking the same solutions that YouTube, Gmail, Google Maps, and all the other Google applications run on. We just took them, packaged them, and started offering them externally, and we applied also all the knowledge, know-how that we have. Therefore, you get the same, in most of the places, you get exactly the same procedures and reliability that Google services get. So a brief look of actually what it means. So what were those technologies that we built over time? I don't want to go into details, but just to give you a gist of that. So there are a number of technologies that we built on the software and hardware side. I'm not sure if you are you aware of any of the names? Raise your hand if you know any of the names from the top of the slide. Okay, good, like 1/3 of the people or something. So those were the technologies that we built in Google over last, as I said, 18 years. The company was founded in 1998. So it's almost 19 years, right? So, and first we just published, the dates are here at the dates of the, I think, publishing the paper. So we published the research papers on those technologies very early. But in 2002, we only published the paper. We didn't publish the actual solution because there were really no infrastructure for that, etc. But we were building this over time, and also the market was growing and adapting. And so you might know that some of those, based on some of those research papers and materials, there were actual open source solutions built. But then later on, we took those solutions and we built the Google Cloud Platform, as I mentioned, right? And the Google Cloud Platform consists of 5 different components, or 5 different areas, we should say. The first one on the top of the slide that I mentioned here is compute. So compute basically means tools that allow you, your developers, to write code and run this code in the cloud. So instead of running your code, whatever this code means on DAS, instead of running it on your physical machine or under your desk or somewhere else, you just get this code and run it in the cloud. Storage solutions are around I want to get my data and store the data in the cloud. And big data is, I want to take my data processing needs. I want to do some data crunching, and I want to execute it on the cloud machines, etc. So, so there's a number of solutions there. As I said, we'll focus on compute today, but I will briefly also cover the other parts. The networking is also an interesting part because, again, when you use Google Cloud Platform networking, use the same networking that Google was building for the last 90 years for all of its needs. So, and I think, I'm not sure if all of the data is published, but if I understand correctly, we are the owner of the biggest network in the world with more than 100 peering locations around the globe, with ability to load balance the traffic for your applications between all the endpoints, etc. And moreover, we have number of peering locations are those points where you can actually connect and enter Google network. But we also have number of data centers that we exposed for for users to run their code in or store their data in. Those green boxes on the slide, they denote a region. When we expose our infrastructure to customers, we typically do it by first saying there is a region, and the region is a collection of independent data centers, which are called zones. The number, and those, why we have separate zones? So zones are typically separate failure domains. What it means? It means that we typically build few buildings pretty close by, one to another. It's important. We want them to be close by because we want the networking to be very fast between them. But they will have different independent network connection. They will have independent power. They will be run by software that's upgraded by Google independently. So it's almost impossible for all of them to go, for more than one to go at once. If we will roll out a new version of software or there will be an upgrade of the cooling system, then we'll always do it to only one of those data centers. One of them can go down, two of them can go down in theory. I'm not sure if it ever happened, but maybe it happened. Two of them can go down in different parts of the world, but within one region, we only touch one at a time. So in Asia, we have two regions, one in Taiwan, one in Tokyo. Both have 3 zones. We have one in Europe. We have 3 in US. We already...
Yeah, we have already opened
Yes,
London.
okay. Oh, yeah. And for this year, we are planning, I forgot the exact number, I think 8 regions more, to open them to public, and that will allow people to run code and store data in various places, which is mostly needed, I think, for 2 purposes. One of them is if you care about having very low latency, then you want to run your code close to your users. And secondly, there might be some legal regulations. So for example, in European Union, there is for a lot of the personal identifiable information, there is an obligation to keep this within the European Union, if I understand correctly. I'm not a lawyer, but that's my high-level understanding, right? So this is why we have regions in various places. Another important thing about cloud platform is that we want this to be allow users to achieve big savings at the same time without having to plan a lot. So many cloud providers work in a way that they ask customers to make some upfront commitments, upfront reservations. We try to not require that because especially for startups, again, this is not the best thing to do. So for example, instead of saying, if you commit to us that you will use X, then we'll give you discount. We have sustained use discount, which means if you will use, we'll give you a discount. You don't have to commit, you don't have to sign any contract. The more you use, the less you pay per hour. We try also to have per minute billing and provide you recommendations to automatically adjust the size, etc. And I will talk more about this later. We also, in the storage space, we also provide different types of storage, and there is the full price one that offers you the ability to access it from every place in the world, etc. But we have also other types like cold line. There are actually 4 classes, if I remember correctly, that allow you to, if you have a data that you rarely need, so you don't have to access very fast. It's just for backup, then it's much cheaper. Okay, so we covered that. And so in terms of data storage and processing, which I think is one of the very important parts of Google Cloud Platform, we have few tools. So I'll briefly cover them. As I said, also there will be a separate session, I think, in either 2 or 4 weeks from now that will have a much deeper description of that. But now I want to give an overview because I think understanding the compute, you cannot write an application without storing data these days, right? You have to store some data. So I want to give a brief overview. So there's again a number of storage solutions for different needs. I think the most basic is cloud storage, when you just store the data files. It's like a distributed file system. There's Cloud SQL, which basically gives you a standard SQL database that's MySQL or Postgres SQL compatible. This is mostly useful for people who want to port to cloud their existing applications that are already built on MySQL or Postgres. There's also Cloud Datastore, which is a highly scalable, horizontally scalable document-oriented database, which basically means you don't, in case of Cloud SQL, you have to choose, I have one server, I have two servers, this is the size of the server, because this is how MySQL works. In case of Cloud Datastore, you don't care about how many servers are behind it. You just write data. If you write more data, you pay more. You will automatically add more and more servers handling your data behind the scenes. Then there is another solution for needs for applications that have higher performance needs. That's Cloud Bigtable. It's again a horizontally scalable NoSQL database where you actually reserve number of servers and you get very predictable, very low latency. And finally, Cloud Spanner. It's a globally scalable SQL database, which has so it provides it's both horizontally scalable like NoSQL, but actually provides SQL capabilities and strong consistency, and still allows you to choose the arbitrary number of servers. Are there any questions or anything? If you have any questions, or if I'm speaking too fast, please let me know, or if it doesn't make any sense to you. Then in the data processing front, there is a number of solutions as well. So if you already have your data stored somewhere in the cloud, I think this is almost always a prerequisite, then you can use Bigquery. Bigquery is a very nice data warehousing solution, again, built on the premise of what we built inside. Inside Google, it's called Dremel, and you can read publications about Dremel. Bigquery is basically a very scalable query engine. You can, when you put your data in cloud, you can write a SQL query that requires thousands or tens of thousands of servers. You can run this query. It might finish in 1 minute or half a minute, and you engage 1,000 or 10,000 servers, and you only pay for this short period of time. So you don't have to start your application. This is because we have a lot of those servers behind the scenes just waiting to execute the queries. And this Dremel system is written in such a way that it has very good isolation between users. So we can write queries from multiple users on the same servers without them one interacting with another. So there is no security risk there. And we are using the same infrastructure to run our queries to analyze ads data, etc. There is Cloud Dataflow for more advanced needs. If you cannot express your data processing task in SQL query, then Cloud Dataflow is a tool which allows you to write simple, typically Java code that just is a sequential code that reads the data, does some processing, like let's say reads the data, filters out all the records that do not meet some property, then group by some other property, and write data somewhere. And you can execute this code on your local machine. And it will take some time. If the data is big, it will probably take a lot of time. But you can take the same code, that's just one Java file with just one set of instructions written in a specific way, and when you push it to Dataflow, then Dataflow actually analyzes what are the stages there of data processing. It will set up separate pools of servers for each stage that makes sense. Sometimes multiple stages of processing make sense to run on one machine. And it will automatically choose the number of servers for that, for each stage of processing, right? First for reading the data, for filtering. So typically if you have reading and filtering, then the same servers will read the data and filter them right away. It doesn't make sense to send to further servers. But if you need to aggregate this by various conditions, then it makes sense to have different pools of servers. And moreover, if you execute this data processing task multiple times, it will automatically learn and tune its execution. And then there is Cloud Data Proc, which, so if you have, any one of you have used Hadoop in the past? Yeah, so quite a few people. So Hadoop is basically an open source version of MapReduce that has been there, written by Apache. So you can run Hadoop. So Cloud Data Proc is basically a tool to take your Hadoop computation and run it at Google in a managed way, in the sense that you don't have to set up servers, install Hadoop there, etc. You just run Cloud Data Proc, and we stuff the servers for you. We adjust the number of those Hadoop servers, and when the computation is finished, we're finished. And very often, you need some tool to actually. So if you have one data set that's you have to process and finish, then that's fine. But very often, people have data that's flowing in all the time, and they need to process this data as it flows in. And for this, you need some messaging queue. So Cloud PubSub is again a managed service that's basically a very highly scalable message queue. And again, similarly to other solutions have heard here about, it's not that you have to say, okay, I want to have 2 servers when I install my messaging queue. Some people do that because they really like Kafka or RabbitMQ, which are very popular open source messaging systems. But then they have to choose number of servers that they need, and if they are not using this, they still have to pay for those servers. In Cloud PubSub, you only pay for messages. We have enough of servers to handle everyone's needs, but you only pay for 1 million of messages that are sent. If you do not send messages, you don't pay for anything. So to summarize and add some additional points. So the advantages of the cloud platform as a whole. First of all, because it's built on the same standards that we use in all the products, that we store everyone's emails in and everyone's calendar entries, it meets number of security standards, and it has our whole cloud security team behind its back. It leverages the global network that we have. It allows you to use all of the big data and machine learning tools that Google has been using in all of its products, including many of you probably use Photos app on your Android phones. If you do that, then it automatically now detects whether there is a cat on your photo, right? And you can search for all the cat photos without even tagging them that they are cat photos. So you can use the same machine learning tools, the same machine learning components in your application. And there are actually a lot of interesting, I think Michał also knows a lot of interesting use cases, how this can be used to build very nice solutions. And it provides a number of tools that allow you to forget about operations, to forget about having to manage your code. And finally, it's very cost efficient, and we'll talk about specifically the compute efficiency later on in this presentation. So now I wanted to jump, we might need to speed up. I will jump to the compute part of the presentation, focus on the compute options. Do you have any questions about what we discussed so far? If not, I'm jumping to the compute. So compute is about running code. Historically, 19 years ago, Google also to run the code had to buy servers or rent the server somewhere. So this is, I think, the first Google invoice for a set of servers in a colo data center. This is how it started. A few years later, it looked a bit differently. This is a photo from, I think, already a few years ago from one of our data centers. And I actually was very lucky. I have joined Google 8.5 years ago, I think, maybe almost 9 years ago. And when I joined Google, I started already in the group working on the software that manages those data centers. And we have faced a lot of challenges that are now visible in the cloud a bit later. So first of all, as we have seen on the previous, some of the previous slides, Google has a lot of locations when we run our data centers. In every location, we have actually multiple such buildings for the reasons mentioned earlier, right? To have separate failure zones, failure domains. In each of those, we have tens of thousands of machines. Each machine is like a horizontal row there, right? And what's even more important here, I think we have around 40,000, I think even more now, engineers building all of those products, meaning building Gmail, YouTube, Chrome, Maps, and actually if you would count all of the Google products, it's more than 100, I think. I think you should be able to list more than 100 Google products. And as we were writing the software to manage that, we noticed that this is effectively few thousand teams building different components. And many of them were facing similar problems. And we were trying to solve those problems for them, allow them, each of them to just focus on the products specific to Gmail. So Gmail should think about emails, and Gmail engineer shouldn't need to think about what happens when a network between two machines breaks, or when there is a disk failure or disk corruption. So we're over time building the tools to automatically manage that, but also, so first thing is to the example that I mentioned is how to prepare for failure, but another example is how to automatically scale your application, how to find out what is the most optimal layout of my components, in which data center, which components should run, etc. So we're building more and more components to make those choices automatic. For majority of the teams, that was perfectly enough. Of course, there will be always some special cases when people want to do some tuning manually. And then we apply the same methodology to the cloud. And specifically in the compute space, we have right now 4 products that differ in the amount of things that user has to do himself, herself, or versus the stuff that we do automatically. Compute Engine is the first solution. That's the most low-level solution when you have the full control over everything that runs inside virtual machine. Then we have Appengine, Container Engine, which do much more for you automatically, but at cost, meaning there are some very extreme things you cannot do. And then Cloud Functions, which is the most automated solution. So Compute Engine, very briefly. What's Compute Engine? Compute Engine is basically virtual machines. Virtual machines, as many of you probably have seen also in other cloud providers, AWS, Azure. I will not go into details of, I assume most of you, raise your hand if you know what a virtual machine is. Okay, most of you raised your hand, but not everyone. So very briefly, virtual machine's ability to, within one physical machine, to start few applications that are called virtual machines, and they actually try to simulate within this machine another smaller computer. And the smaller computer effectively can have different operating system, so different applications installed, etc., and all of them are completely independent. And you can rent such a virtual machine from a provider. And there are many providers. So I will not go into much more details about these basics, but I want to highlight few features specific to our cloud. One of them is live migration. So actually, this animation has a brightness problem, at least here. So what it shows is that I think we're the only public cloud provider that has this capability. This capability is a big public cloud provider. This capability is ability to move a virtual machine from one physical machine to another one without stopping the application inside and without users of this application noticing that their application has actually moved. So we do it by starting a part of this application on another machine, then slowly migrating the traffic and shutting down, migrating the contents of the machine, then migrating the network packets coming in and out, and then stopping the old application. The core. Why it's important? It's important because the physical machines on which it runs, the virtual machines run, they will go down from time to time, or we have to upgrade them or send them to repairs, or they also run some operating system that has security vulnerabilities that has been announced, and we quickly have to fix them, apply the fixes. And what other cloud providers will do is that they will send you notification. Your virtual machine is running on a physical machine that will go down. Either restart your virtual machine or we will kill it for you within next week, 2 weeks, I don't know. Depends on the situation. Not here, so we seamlessly migrate it, and the only way to notice that it happens is that if you run a very advanced performance analysis, then you will notice that the machine might slow down a bit for a short period of time. Then another special thing is that, contrary to most of the other cloud providers, GCE supports so-called custom machine types. What does it mean? So most of the providers only support machines with 1, 2, 4, 8, or 16 cores, so just powers of 2, right? But not and also the same with memory, and also not all the combinations of CPU and memory, right?
That means in general that if you want to double your memory, you have to double your CPUs, or the other way around. With Google, it's possible that you just select that number of CPUs that you need and that number of RAM completely independent.
Yeah, exactly. Or even worse, if you need 5% more memory, then you have to double your memory and double your CPU at some point, if you are close to the border. With GCE, you can choose an arbitrary amount of RAM and CPU. And on average, it means 19% of savings, as I mentioned here. Then you don't, but of course, then people will say, but it's often difficult to perfectly choose your size of the machine. But here we also provide you with recommendations, meaning we analyze the workload that's running inside the virtual machine and tell people you can save $101 per month if you actually adjust the machine size to this exact amount that we have computed based on the behavior of application. And as a result, all the boxes here are perfectly aligned to the workloads inside. It doesn't mean just to the current load that the virtual machine will analyze the history, find the peaks, patterns, etc. And finally, the per minute pricing, which is also atypical. Most of the providers, I think, charge per hour, means that the shorter your workload is, the more you save, because you just pay for 1 minute after 10 minutes. But even with very long, like 6-hour workloads, you very rarely end up on exactly the end of an hour. So the savings are at least 10% in practice. And one more part of the offering that's also very special to our platform is called preemptible virtual machines. Preemptible virtual machine is for people who would like have a lot of processing to do. Some big data computation, maybe visual effects rendering is a very particular example because it uses a lot of CPU, or some financial or biological simulations. But you don't want to pay a lot. You don't want to pay for the full-size machines. So you can use preemptibles, which are cost around 30% of the cost of a normal virtual machine. The only constraint is that it can run only up to 24 hours, so you cannot use it for something that runs forever. And it can be killed from time to time. It happens rarely, but sometimes it can be killed, and you have to restart your computation. Of course, you don't pay for that. But so you cannot use it for something that has to be running 24 hours by 7. So typically not for serving your front end to your customer, but very often if you want to do some just background computation of preparing some reports, etc., that's perfect, and that's much cheaper. And it has a predictable cost, because again, I think many of the competing solutions here, they use some kind of an auction. So they are saying, oh, we have some machines that no one bought for a full price. We will put them on auction, and sometimes you buy them very cheaply, but at the same day, the same analysis actually might be even more expensive on those machines than if you buy a typical virtual machine. So you don't know what price you'll get tomorrow, which is not the case here. And one more thing is that, of course, virtual machine would not survive. You cannot use a machine without the disk attached to it. And again, we have few solutions here. The most typical is a standard persistent disk. So it's a typical rotating disk-based storage, but it is remote in the sense that it's not a physical disk attached to this machine on which your code is running. It's a replicated disk running on multiple remote physical disks. Therefore, even in the unlikely event that the physical machine on which your virtual machine runs will crash, will have an outage, which sometimes happens, your data is never lost because it's replicated in at least 3 copies, I think. Then there is a variant of this which uses SSD disk, so which is much faster, gives much bigger, much lower latency. But what's interesting in terms of throughput, it's also I think what makes it different from other cloud solutions is even ignoring replication, so multiplication by 3, one persistent disk is not mapped to one physical or 3 physical disks on other computers. It's actually very often mapped to many more disks. Therefore, the bigger space you get, the bigger disk you choose, the more physical drives you store your data on, which means you have more spinning disk at your disposal, which means it's faster and faster. So the bigger the disk, the faster it is. So you get bigger and bigger throughput with the size. And you can also get local SSD. Local SSD means it's physically running on the same machine that your virtual machine. So it has the best latency, the lowest latency to your data. However, it comes at the expense that it doesn't provide the reliability. So you should not store, because if the physical machine goes down, then your data goes down. Therefore, you should use it mostly for temporary data that like intermediate result of computation, because once every few years you might lose something. And so what we discussed here is like the lowest level in building blocks. Now, on top of that, many people might say, okay, I still need virtual machine, because I will have my own special version of operating system. I want to run Windows, I want to run macOS, or I need a special driver or special configuration of something for my Oracle database. But I don't want to manage those machines. I know that I need a special machine, but I don't want to manage them. Specifically, I need 100 of them, and I don't want to think about them. So managed infrastructure is a set of tools built in Poland, completely built out of our Warsaw office, by the way. And I think a lot of things here are built out of Warsaw, if you're interested. So we have a number of engineers that are the authors of that. But so managed infrastructure is a set of tools that automatically manages virtual machines for you. What it means? So first, when most of the people, when they use Compute Engine or similar solution, they just manually create a virtual machine, connect to it, and manually install some software there. And if it works, hooray, we have a working virtual machine. But then they think, okay, I need a few more virtual machines like that. So here, they can start using managed instance groups. This is the right moment. So you can say, I want to make a snapshot of this virtual machine, and I want to ask for 3 identical virtual machines. Great, we'll make a copy. No big deal, right? A simple for loop could do that. But if you it's actually more than just a simple loop to create 3 machines, because if you're worried about the reliability of your software, then the machines can go down or your application can have bugs. So in the managed instance groups, we have a feature that's called Auto Healer that will automatically observe your virtual machines, and if they are going down, it would automatically heal them, fix them. Then, if your application is growing, you have more virtual machines, you have to add, because in the peak on Friday evening, you have a lot of users. But you only have them on Friday evening, and most of the day, you have much less of them. So you can enable autoscaler, which automatically adjusts the number of virtual machines based on various conditions. And those various conditions are depending on your application. It can be CPU utilization. It can be automatically scaled based on the load balancing information, for example, based on number of queries, or based on some metrics exposed from your application. Or actually based on the number of different metrics, so you can specify I want to scale based on a few things, and just you take max out of it. Then once you have your application running, you might say, okay, it's running, serving a number of users, but I have a new version. And you don't want to stop all of the virtual machines and just provide a start a new version. You have your users running all the time. So here we also have a tool that's called Updater. You provide Updater with a new version of your application. It will automatically roll out it to your virtual machines one by one, and observe if your machines are healthy. If something is wrong with your new version of application, it will stop. And if you need really high availability, then as I mentioned earlier, you shouldn't be running in one data center. You should choose multiple data centers to be protected against fires, against power breakages, and etc. So you should run in multiple data centers. You can do it your own, or you can use regional managed instance groups, which will just automatically spread your load between multiple zones in one region. Multiple zones in one region specifically, because you can spread between 3 zones in different regions, and you also might get a good reliability, but because they are far away, the network is slower between them, and it's pretty costly. If they are within the same region, the network is fast and much cheaper or free in most cases. And then finally, with the machine right-sizing that I mentioned earlier, we can automatically adjust the size of those machines. And I think I'm behind on the time. I need to speed up significantly. So that's a summary. I will not go through it to save some time. So the second solution, so I'm finishing with Compute Engine. If there are any questions about Compute Engine, let me know now, or I will move forward. You can also ask questions at the end, but feel free to interrupt at any point in time. Appengine. What is Google Appengine? So Google Appengine is different from Compute Engine because it allows users just to focus on writing the code specific to the application, but do not have to worry about operating system, libraries, and things like that. As a result, it allows to build application much quicker, and you don't have to worry about most of the problems about machines going down. You still have to worry about bugs that you wrote in your application. but you don't have to worry about bugs, problems with the machines, because Google site reliability engineers are watching for that, and if there are any problems, they will automatically handle this for you. And it will automatically distribute your application across the globe and provide high availability this way. And yeah, I will also quickly go through that. So the also specific property of the Appengine that makes it different from many platform as a service solutions is that it doesn't run on virtual machines, as many of the platform as a service solutions do. The running on virtual machines has a number of advantages. It scales, but by default, so Appengine can run on virtual machines, but by default, the standard version of Appengine does not run. It runs multiple smaller, lightweight virtual machine-like clones on one server, on one machine with one operating system, which means it can scale way faster. It can start new virtual machines way faster. If your application is very lightweight, you have a simple Go or Python application, then it can start a new instance of your application below half a second. While booting up a new virtual machine takes at least a half a minute. So how to choose which one to use when? If you have a complex batch processing, you should go for infrastructure as a service, so Compute Engine. If you have a web workload and mobile backend, definitely platform as a service is the right solution. If you just don't want to worry about all the details, yes, then go to platform as a service, so Appengine. Then if there are some special capabilities that you might need to analyze whether you need them or not, if you need root access to virtual machines, then typically you should go to virtual machines. If you need C++ libraries or some special other features, you need to go to infrastructure as a service. If no, then platform as a service is always easier to manage, less things to worry about. However, there is a variant of Appengine that's called Appengine Flex that actually bridges those two worlds. It still provides you automatic management of Appengine, but it allows you to run any code because Appengine allows you only to use specific languages. That's critical to allow this very fast startup. So Appengine Flex basically runs Appengine on virtual machines. So you can run arbitrary code, you can use any libraries, you can SSH to your machine, but you still get our management to upgrade your machines, give you updates of the operating system, and apply the security patches. And here is a comparison of both those solutions. I will not go into details, but in short, standard is much faster. It will scale to 0, so if you have no users, it will will turn off the last server, and it will turn it on back very quickly when the first request comes. It means you don't have to pay anything at all at night when you have no users. With Flex, you always have to keep at least one machine running. And both of them support all the standard programming languages like Java, Go, Python, but Flex supports more. It supports .NET, Ruby, etc. And Appengine scales very efficiently, very quickly. Just in 2014, we published that we supported 28 billion queries per day. An example of that, of a very happy user of Appengine is Snapchat. I think most of you have heard about Snapchat or have kids. I have kids that use Snapchat all the time, so to send photos. And Snapchat is a typical case of a startup that just used Appengine because they said, I will have this idea of sharing photos that do not stay forever. But we don't want to worry about anything else. So they just started with using Appengine. It was very easy to write the first version. And they said, we'll worry about the rest later. But they didn't have to worry about it ever. And they scaled on Appengine until today. Today they are sending, I think this data is also a bit old. I think it's bigger now. 700 million photos and videos each day. And all of this goes through Appengine. Okay, so as a result, you have a spectrum of choices. You can go just with core compute engine and run your code there, but then you have to manage your code, build application, choose the operating system, distribution and version, etc. You can use and then you have to manage the number of machines. You have to choose the number of machines. You have to choose when to upgrade them, etc. You can use manage infrastructure that relieves you from the management of machines, automatically chooses when to add a machine, when to fix it, but you still have to write your binary. Then you can use Appengine flags, which automatically manages more things for you. And then with Appengine standard managed runtimes, you don't have to write the whole application. You just write some special parts of the code that are executed when a request comes in, and you'll see a demo of that in a minute. So,
thank you, Jarek. After this large portion of the theory, let's move over to code labs and to demo. For this session, we have selected a number of code labs, and we thought that it's of course beneficial to see how easy to run the demo during the session. But we actually thought that it will be much nicer for you if you can actually go home and replicate the demos yourself, looking at how easy it is to build and run the application. So you have the resources here. We will do the first demo about the Appengine, and you can go directly to the code lab at the bottom, which is Appengine code lab. Or if you would like to explore more code labs for other technologies, for other services that Google provides, you have the Code Labs developers, google.com, where you will find all the other code labs that you can run and follow at your own pace. So now I'm going to switch over to the environment that will serve as our demo today. And here we have the Google Cloud Platform console. I'm logged on into the campus demo project. This is one of the many projects, so you can have multiple accounts, and under each account you can run multiple projects, so that all your applications can be made separate, depending if you run them for your customers or internally. Even if you run them internally, you might be interested in the metrics per project, so we can run multiple projects on Cloud Console. Today we will now in that portion we'll actually talk about Appengine application and Compute Engine application. So we will see how to run each of those in the console. So first of all, in order to start the application, we need to have the source of our application. We will not be writing the code today. We will just deploy this code. So in order to allow you to work with Google Cloud Platform, you can download onto your machine the special SDK, Cloud SDK, that will allow you to run the commands and perform some actions on the console. But actually, maybe first, how familiar are you with the console for Google Cloud Platform? Have you ever checked the console? Okay, just few of you. So the console is built this way that after you log in, this is the dashboard that shows you the most important information about your project. This is the project name, some information about the Compute Engine or Appengine. There is nothing, we are not running an application now. And the very important thing is that the console is very consistent. So any point start any service you want to run in the cloud platform is available via the menu on the hamburger. When you click on the hamburger menu, you are presented with all the services that you can start in the console. So here you will find what we are going to discuss and what Jarek was talking before. So Bigtable, Datastore, and so on. Now, because we don't want to use our own machine to actually invoke any command lines, Google Cloud Console comes with the Cloud Shell. Cloud Shell is a special machine that is spooled by going to the link to activate the console shell. And this is a special virtual machine. This is free, and this is being saved every time you quit the console. So if you are not using the machine, it will actually save all your data in it, and it will sort of hibernate until you need it next time. So I'm now spooling this Cloud Shell machine, and here we will be working on entering the code and deploying the application. Before we do that, Google Cloud Platform comes with a special service that replicates the functionality of GitHub or Bitbucket and other repository services. So in order to start working with our application, we need to take a look at the repositories and check if we have any repository. At the moment I'm checking, we are looking at the repositories. There's no repository created, so we need to create a repository on Google Cloud Platform, and we will name this repository default. This will be the default repository that can hold any of your code. This repository can be replicated from either the local repository or from any of the cloud repositories from other services, like I said, from GitHub or Bitbucket, and you can hold the code in Google repository and deploy applications using those repositories. So now we have this repository. This repository is empty, and we will actually clone and push changes to this repository. So in the Cloud Shell, I'm going to create a directory. This directory will be holding the local version of the repository, so I will just name it local repo. And this directory, we will enter this directory. I will use Midnight Commander. This is not very professional, but hey, we have this this tool, and we can always take a look at what's inside and see that this repository is empty. Once we are inside this this local repository, we need to get the code for our application. As I said, we will not be writing this code. We will actually download this code from the GitHub. So I'm going to type the repository from which we'll take the code for our application. Once we, I'm sorry. Sorry, we have to initialize the repository first before we actually can download the code from external repository. So we need a special tool that is part of the Cloud SDK, which is called gcloud, and we need to initiate the repository locally. So we need to initiate the repository first, and once this is initiated, it will allow us to actually pull the data from the previous step that I have tried. We have now the content of the default repository. It's now almost empty. There is just information about the GitHub repository, and now we can clone the content of this application. As you can see, now we have a couple of applications in this repository. One is Appengine, the other is Cloud Storage, there's also Compute Engine and Container Engine. We'll focus on the Appengine, but first we want to push the content of this local copy of this repository into this default repository on Google Cloud Platform. For that, we just use the standard git push origin master branch, and it will upload the content of the local repository onto the Google repository. If we refresh the top parts of the source repositories, you will see that we have those repositories filled in from our local copy. Once we have that, for this demo, we'll focus on the Appengine. And if we look at Appengine, this is a very simple application that will serve as the storage for the books we own. The name is Bookshelf. This is the Python application. Python was actually one of the first languages supported by Appengine. You can select some other languages. Jarek has mentioned for the standard, this is Python, Go, or Java. With the Appengine Flex, you have more choices. You can also write and host applications written in .NET, in Ruby, and some other. With the Appengine, what might be interesting for you to know is that you can also write applications in PHP. So if you have, and PHP is quite popular, you can create the application in PHP and host it on Appengine. With the Bookshelf application, we have some of the important files that describe the application. They are held in the subfolder named Bookshelf. You will find there the templates for the way the application will look like, so the UI of the application, and also some files that will actually decide on how the data will be stored in the services. For the purpose of Bookshelf application, we'll be actually storing the data in the Datastore, Google Cloud Datastore. This is, like Jarek said, a non-SQL database, the very fast one, the one that replicates horizontally, so is best used for an application demanding increased performance over time. And we will store our books in this application. Since this is just the standard Python application, we have probably some of the requirements that need to be fulfilled in order for this application to work. We can take a look at the file named requirements, and here we have the two requirements to be fulfilled. We need Flask and GUnicorn. In order to work and to fulfill those requirements, we need to install those modules into our repository. We enter the Appengine repository folder, and we install the requirements. We'll use the PIP tool to perform that operation. PIP install -r requirements .txt -t, and we'll hold those items in the leap subfolder. Now we need just to wait a bit until those required modules will be installed. if we go to leap, we will see that the Flask and Unicorn, together with some other modules that are required by those two modules, are installed locally. For Appengine, we have also a special file that is called Appengine Config.py, and it specifies those additional libraries that are needed by our application. In this case, this is everything that is contained in the lib folder. So that informs our application where to find our libraries. Now, when we have the application configured, we are left with deployment. And here I would like to introduce a very interesting tool that is now part of gcloud application. When you have command lines, and gcloud is a really nice tool, but actually the one that requires a lot of different options and parameters. gcloud contains a very nice shell application that provides you interactive help on the commands that you are going to execute. So in order to enter this shell, we type gcloud alpha shell, and we are presented with the interactive tool that allows you to enter any operation, and it provides interactive help on what you are trying to achieve. So if I'm deploying the application, I need the option app. And below that, I'm getting the instant help on the format of the operation that I'm trying to perform. And in this case, I'm executing the command app deploy. So it will execute the deployment of the Appengine application on Google App Engine. Here I'm presented with the configuration. I can change the way everything is configured for this application, but here it is correct. So I'm now performing the deployment of the application. It uploads the files to the Google App Engine, and once the upload is done, it will actually allow me to start the application on Google App Engine. As you can see, the upload is done. The application has been created and is accessible via the standard link. The link is the name of the project. In my case, this is gocloud-campus-demo.appspot.com. Now, on the Cloud Console, we can go to the Appengine to Appengine dashboard, and we will be presented with the information about the application. So here we can see the services running. We can see the version that is running of the application, and any instances that might be running here. At the moment, since we just deployed this application, there's no instances running, so we can go and start the appspot.com application. It will spool the instance. If we go back to the instances, we will see that there is now a single instance running. It shows you what is happening, how much memory it uses, and we have our application started. Like I said, this application is the simple bookkeeping application, so we can have our books cataloged here. We can add the book, and we can, for example, add one of the books I read recently. This is Darknet by Matthew Matter. I think this book has been released in 2014. Demo on campus as a description, and we have our book created in our application. It doesn't hold the image yet, but it allows us to see the book, edit the content, and enter more books if we would like to. As you can see, the application is live. That means that anyone can access this application under gocloud-campus-demo.appspot.com, and you can also add the books to this application. The beauty is that in a very simple steps, we have actually spooled the application, and we don't need to spend time on configuring the operation system, web server, on selecting the parameters to serve our application. At the same time, we can see what's going on. We can deploy multiple versions, and even we can split the traffic between those versions if we want to see the old and new version of the application. And also Appengine works for us, so the non-used instances will be automatically closed, so your application doesn't use too much of the resources if nobody is actually using the application. So you save money, and with Appengine you also have some free tire on the performance, so you don't need to pay if your application is very lightly used. So this is ideal for loads where you don't want to spend your time actually configuring and taking care of the servers on which your application runs, and this is ideal for increased load when you have, like in the example Jarek gave you, you have the peaks on Friday, and the rest of the week the application is basically not used by anyone. We have actually built our first Appengine application in 2012 when the Appengine has been created, and we have operated that for a company that was doing the purchases for factories, and this application saved them enormous amount of money because it was only running when they were running the negotiation sessions, and after that it was just waiting for users to come and start using the application. So that concludes the Appengine demo, and now I'm going to show you exactly the same application, but this time deployed using the compute engine instead of the Appengine. So we will actually create the application that will be run on the virtual machine. And with the Cloud Console, you can actually click on anything and create the virtual machine using the UI, the console UI. So selecting the parameters for the machine you want to run, you select one of the zones that Jarek has been discussing. So like I said, we have now two regions in Europe. One is located in Belgium, the other one is located in the UK. And you can select one of those regions. You select number of CPUs, and you can get the standard memory, so the types where the CPUs are tied to memory. Or you can decide that you want the custom type, like Jarek was showing, and then you can manage the memory and CPUs independently by using the sliders. Of course, Google suggests some of the values, but you can basically disregard that and run whatever you need. With the virtual machines, it is quite interesting to know that you can attach the GPU. So if you have the GPU-intensive operations, you can actually attach such GPU unit to your virtual machine and perform those computations using GPUs. Here, with the demo, we will actually create will create the machine using scripts, because normally the UI is when you want to experiment, but when you are actually into serious computing, usually you script those operations, because it gives you ability to perform those operations many times for different projects from just using the pre-built set of scripts. So here, with the compute engine, we will actually spool a machine that will deploy our application. But we'll do it in a bit different way. So any virtual machine that you spool on Compute Engine, you can write the startup script that will perform some operations on this machine. And here we will go to our repository and select the Compute Engine option. And for Compute Engine, we can actually take a look at the startup scripts, and for those of you that are familiar with bash scripts, this startup script will actually create our application, replicating from the repository. It will clone our repository, and it will update the environment, installing necessary software, and then it will start this bookshelf application using the startup scripts. So let's build this machine. First, you need to remember that with the startup scripts and the way that software is downloaded, it is not the most efficient way to start applications regularly, because you can actually build your image with your application already installed, and using that image you can spool the machine. But here, for the purpose of this demo, actually the startup script will download the software for us and do it the moment machine starts on Compute Engine. So I will type some of the commands to start the machine. First, we need to decide on which zone we want the machine to be started. Here I will select region, European region, and we'll select West 2 zone C. So it sets the environment, the way that the machine will be created in the zone. And now I will need to define the machine that needs to be started. So again, the gcloud compute command, we need to create the instance. So we create an instance that will be just named bookshelf. And we need to specify some parameters which will define this virtual machine. So the image family will be Debian 8. Next, the project from which the image will be taken. So image project. Next, we need to define the machine type. We have some predefined machine types, so instead of specifying each time how many CPUs and how much RAM we need, we can define the machine type, and we have the nano machines, so the smallest ones. Then we have G1 small machine. This is the machine that I'm actually selecting now, and then we have so-called standard machines. If you are not using the machine type, but you need the custom type, then you define number of CPUs and the amount of RAM that this machine is going to hold. I need some additional information here, so let me type that. I will go quiet for a second once I type that information. here I defined the startup script that is going to be run when the machine starts, and it will install the software for us so that it's deployed the moment machine is ready for use. Okay, now the machine is going to be created. Sorry. Of course, we need to change the repository in which we are to Compute Engine. And here we should be able to spool the machine. It's going to be executed at the bottom. At the same time, we can go at the top and take a look at the Compute Engine view. And here we can see the machine being started. At the same time, at the bottom, we can see the information about this machine being created. We can see that this is indeed the G1 small machine with the internal IP address and external IP address for this machine. So we have this machine started. Now we need to create one more thing. We need to allow the traffic for this machine to reach this machine. So Google provides the networking component for the whole cloud platform. And here we define the firewall rules for this machine. So those firewall rules can be actually created via script or can be created using the UI. In this case, I will actually create this default allow HTTP on port 8080 rule, and here we can decide what is the target tag. We can specify the target internal networks, but we can actually use tags, and since our machine has been created with the tag HTTPS server, we can actually define that this rule will allow the traffic to reach this machine on port 8080. In this case, we want to allow any traffic from the world to reach this machine, and here we can specify the protocol and port on which we allow this traffic to reach the machine. So I'm creating this rule. This rule will be created, and only then the traffic on this IP address will be allowed. This IP address is ephemeral, so it will change every time the machine will be started. But of course, you can also create the static IP addresses and attach those static IP addresses to your machines for executing the for accessing the applications. So here I can see that our application has been started. This is now running on Compute Engine, and in this case you can see already that those books that existed before are still being used because we are using the Datastore. So again, we can create another book. I will just type it here. I will type the today's date, sorry, and create it during demo. Yep. So we have another book added, and our bookshelf actually contains a couple more books. If you want, you can also contribute to those books just by going to the IP address 35.189.104.133 on port 8080, and there you will be able to add the book to your collection. Yep. So if you want, you can test it. That concludes the Compute Engine demo. Now we wanted to show you the other part, but before that, before going to other demos, I'm going back to giving the stage to Jarek again for some of the text explanation for what we are going to see later on.
Thank you. Thanks. That has been a lot of content. I wanted to quickly do a pulse check in the room. Do you think that we have not enough details and it's boring, or you have too much details and it's difficult to follow some of them, or maybe it's perfect? So raise your hand if you think we have too many details in the presentation. Okay. Raise your hand if you think we have not enough technical details and you knew all of that. Okay. There are a bit of people in both groups, but more in the former. So I think we'll try to skip some of that. I was wondering, maybe I wonder if container engine demo is something that we can also shorten.
Yes, of course. Just continue with the slides, and instead of building this application on the computer demo, I will show something a bit more interesting.
And maybe the cloud functions also. Yeah. Okay. So another product in this space is Container Engine. So it's another tool to run your code in the cloud, but using slightly different principle. So using a container. So raise your hand if you know what is a Docker container. Okay, again, 1/3 of the room or something. So try to explain what it is. So historically, 15 years ago, when a company would have its own data center or maybe set of few machines, in Polish called serwerownia, they would have few of those machines and few applications there. And there will be an HR application or payroll application or a finance and accounting system and some system for orders, etc. So we have those different applications, and they will be all. And you typically don't want or need a separate server for each of those applications, because that would cost too much. So people would install multiple applications on one server. But this has few disadvantages. First of all, those applications, especially if they're coming from different providers, they might have some bad interactions. They might require different versions of your operating system, or different version of libraries, or different configuration of your operating system, different configuration files. And either you cannot install both of them at the same time, or sometimes an upgrade of one of them can break the other one. So that was bad. So people introduced those virtual machines that we have talked about. Virtual machines within physical machine allow you to create multiple independent machines. In each machine has perfectly shaped size. So if you have a physical machine with 8 CPU cores, you can split it into 4 virtual machines. Each of them have 2 or any split that you want. And they cannot interfere, they cannot use resources, and also they have different version of operating system and different version of all the libraries. They have different configurations, so there is no interaction between them. But there is a problem. It causes some problems, at least 2 problems. It works very well, and many companies work this way and still work this way, even running virtual machines inside their data centers. But first of all, they are pretty hard to manage. You have to install operating system on all of them. You have to do a number of things, and they are very expensive in the sense of it takes time to start a virtual machine, and it uses a significant amount of memory and CPU resources. So people are thinking about trade-offs between those 2 solutions, and Docker Container is a solution that's somewhere in the middle. So Docker Container is a small virtual machine like a thingy, that runs, so you can take your machine and run multiple containers. They are isolated between each other. So application running in one container cannot see the other applications, cannot talk to the other applications unless we allow them. However, it doesn't have its own operating system. It actually sees the operating system from the machine on which it runs. But all the libraries, all the configuration files are within the container. So some of the stuff is shared between the machines, which is basically the host operating system, but the rest is per container. What it gives us? It gives us the ability to, it's much cheaper. The overhead of running those is way lower, orders of magnitude lower. It's much faster. A container can be started in tens of milliseconds instead of half a minute. So this is the idea of a Docker container. And one more aspect of a Docker container is because it's so easy to start and it provides you this isolation, you can also create this on your desktop machine or your workstation or your laptop, enter the container, install your software there, take a snapshot, we call it a container image, and then take and restore this container image into any server in production. And this way push very easily your software from your machine to the production. You could do the same thing with virtual machine if you would run virtual machine on your local machine, but that takes much more time and uses much more resources. So the Docker containers, they were developed, became very popular in the last few years as a tool to deploy applications. But if you have a lot of containers and a lot of servers that you need to load on them, then first of all, it takes a lot of time and it's very difficult and it's sometimes risky. You can have various problems with containers. So you need another tool on top of that that helps you manage multiple containers. So how we can do this? How we can manage multiple containers? And the solution that Google came up, which was actually based on how we manage everything inside Google. And Google internally actually uses containers for almost 20 years. We do not create separate virtual machine for our workloads. We do not need that. We use containers. So we built, based on our experience, we built Kubernetes. Kubernetes is an open source tool to manage container orchestration. So by orchestration, basically mean managing multiple containers and putting them on machines. So how it works? We have a basic, one basic concept in Kubernetes is a pod. So what is a pod? So container is basically one application that you can, typically you create a separate container for each application. If you have for example, your payroll system talking to database, you'll have a database in separate container and payroll system in separate container and separate container image. But very often you want them to run together on the same machine for some reason. So pod is basically a collection of containers that you want them to run on the same machine. It doesn't mean they will be the only ones. Maybe the other containers also run on the same machine, and it doesn't matter because there is good isolation. But they should always, if you have a pod with two containers, they should always come in pairs, and they should always be moved between machines together. Simple example is you can have a web server that's serving your customers, even static content, and you have a separate application that's called, in this case, data pooler, that basically pulls the files, pulls the web pages from some database, from cloud storage that Michał used in his demo, or from other place, and pull it locally to local disk, such that the web server can serve those pages. And this data pooler can automatically update it. Or the data pooler can also export some logs from the machine. And then the whole idea of Kubernetes is that we have a number of machines that are called nodes that are used to run pods, and we have one master machine. Master machine can be also replicated, but logically it's a one thing. So you talk to the master and say, I want to start this pod. And the master will look at all the nodes, will look at all the ships, and we'll see on which ship there is a space for the container, and we'll put the container there. So in this case, we have the middle machine has space, so the master will put it there. But then if the machine goes down and anything happens, the Kubernetes will automatically move this pod to another machine. Okay, that's fine. You don't have to worry about where you have space for those pods. But if you have what to do if you have a lot of them. So there is a number of different tools for replication. I'll just mention one example. There's a concept called Replica Set, which basically allows you to say, I want this is my template. Template says this is how my pod should look like. This is what application should run on. And I just want four replicas. It means 4 of them will be started on some machines wherever the space is. If one of them goes down, the system will automatically recreate another one. Either your application can crash, every application has bugs, or the machine on which it runs can crash. Doesn't matter. The replica, if you create a replica set, it will automatically manage the number of those. There are also other tools to manage multiple copies of your application. For example, you can say, I want to have 1 copy of my application on every server. So I don't know how many servers there are, that many copies I want. So for example, if you have some application that monitors your servers, right, then this application should be running on every server. And then another concept is a service. So if you have multiple pods, typically because you are using some kind of replication controller, if you have let's say a very popular application, you need multiple copies of application to handle all of your users, but you don't want all of the client application to have to understand, okay, so there are 5 copies of my application, which of those I want to talk to? If there are 6, then which one? How to handle that? How to handle that? So the service is a solution to that problem. Service is a concept which says, I define a service as a collection of pods. So this is my logical service and application. And I say, I want to create a DNS name for this service or an IP address, virtual IP address. And then whenever a client will talk to given virtual IP address, the system will automatically route the traffic to one of those pods. If you add more pods, or if some of them go down, the system will automatically adjust it, and the client doesn't have to notice that more servers handling this were created, or some of them are down. And now an example of a customer of Kubernetes, Pokemon Go. How many of you have heard about Pokemon Go? Raise your hand. If you or your kids have heard about Pokemon Go. So Pokemon Go runs on Kubernetes. And just before, that's actually a story of what happened with Pokemon Go. Yeah, it was popular. It was popular around the world. So when just before the launch, the Pokemon engineers made an estimate of what will be the load. And they measured the load in the terms of number of database transactions. That's some unit, right? And this orange line shows the estimate of their amount of transaction based on the data they had. But they said, okay, we have to be prepared for the worst or the best case, depending how you look at it. So they wanted to test their application against 5 times bigger load. So this is the orange line here. And what happened was the green line. I think this is a graph of first few weeks of Pokemon Go success. This is when most of the growth happened, right? And the system has grown 50 times over their initial estimate. But they didn't have to do any significant changes. They had to do some small optimizations, but they just automatically scaled. The system automatically scaled and adjusted. They just were adding more pods, a replication controller adding more instances, and the services were routing traffic between that. And within few weeks, they were able to all of the time handle, or most of the time handle all of the incoming requests. Now, probably most of you have heard or remember Nasza Klasa, which was not running on a scalable public cloud, and Nasza Klasa at some point became more popular than they wanted, and I think it was down for a number of days, right?
Yeah. This is everything about the containers.
No.
Yep. Sorry.
No. One more part. So one more interesting part about sorry, I thought I wanted to add something. Important part about Kubernetes is that it's an open source software. It's an open software, not only open source, but open in a number of ways. What it means. So we wanted to focus on the fact that it's, first of all, that it's a portable system, so you can actually run Kubernetes not only on our cloud. You can run Kubernetes in your data center. You can run Kubernetes on AWS, Azure, on your laptop. And we also, the whole abstractions, the way you use Kubernetes is independent of what cloud it runs on. Therefore, as a result, you can actually take the take your deployment that you first had in your data center and move it to cloud with almost none or very little changes. Or you can move between the providers. If one of the providers became cheaper than the other, you just put it on, you just take it and run it somewhere else. And additionally, it is open source. It means many people, everyone in the world can start contributing to it. So what is the result? This is what I just mentioned to you is basically theory. What it means in practice for the system. So first of all, over time, despite the fact that the Kubernetes is one of the fastest growing teams at Google, and there are more than 100 engineers working on Kubernetes, the community of people actually working and building the system has been growing faster than our team. So right now, Google is out of 42% of the Kubernetes. While the second biggest contributor to Kubernetes codebase is Red Hat, it's only 7%. And there are a few other companies that you can see here that are even smaller, but 45% are basically very small companies or individual contributors. It means that this is really a system that's open, and many people having different needs are contributing to it. So we know that it meets needs of vast majority, great group of people. This is the graph of number of people actually working on Kubernetes, contributors. We have right now more than 1,500 contributors working from 15 time zones. This is a graph of number of people active in a given week, if I recall correctly. So this is exceeding 200 already. And the other aspect of this is that right now Kubernetes can be run in 46 different technologies, 46 different environments. Our cloud is just one of them. This includes 8 different hosting providers, which means companies that run Kubernetes for you and manage it for you, or you can run it on premises, which means in your data center. And Google would have no ability to even test it on those configurations, but definitely wouldn't have time to implement all of those variants of Kubernetes running on different ecosystems. But thanks to the fact that we have opened it and in the large community, we reached that. So
okay, so we have prepared the demo for you, and this demo, of course, you can follow. There are 2 versions actually. The first version is the generic CP100 container engine code lab that you can follow, but since there are some changes into the commands that need to be executed, we have prepared also a dedicated up-to-date version that you can find under this lab. But since you are not really that keen on looking at the boring command line, and I totally get you here, I would like to show you the way we can better understand why containers are good. This is actually a demo that has been prepared by one of the Google engineers, but it shows why containers are useful. Do you know the whack-a-mole game where you actually try to smash the mole with the mallet? So Kubernetes is sort of that thing. So we will spool a number of, we have 2 nodes. And on those nodes, we are spooling a number of pods. And now we can whack those pods, so trying to kill them. And if you are quick enough, you can even try to disrupt the service. They are started automatically, so every time one of those pods gets killed, the new ones are created. So this shows the whole purpose of running containers. Even if your application fails on one server, it will be started immediately on the other server, so that you can continue working. So that means that the infrastructure is more independent, and you have more stable performance and ability to run those options. So this is just an example, but it gives you better understanding what containers do. And those pods are deployed automatically. So we just define number of pods that should be running on a specific node, and then Kubernetes actually controller does everything else. So it just takes care of your machines the way that you have your services available.
Thank you, Michał. Can you hear me? It sounds like, oh, okay, thank you. So in this, as you have seen in this demo, whenever Michał was actually clicking this button, it was actually killing a container instance, killing an application, and still it was restarting within 1-2 seconds or something.
Yeah,
so this is
like
why restarting a virtual machine would take much longer. And not even talking about fixing a broken physical server in your data center, when it takes typically days to get a replacement component. Okay, so now the last part. The last part is about Google Cloud Functions. So Google Cloud Functions is the highest level platform here, which by highest level I mean it does the most stuff for you. So you have to care about the least things and write the smallest amount of code. So what Cloud Functions is? So Cloud Functions is a serverless platform. So serverless means you do not know what a server is. You don't have to think about it. Appengine to some degree also is serverless. Compute engine and container engine is not, because you see servers. And it's for building functions. So you don't build applications. You don't build binaries. You just write simple function. Function takes some input, does something, returns some output. And it's a platform for building event-based functions. What does it mean? It means that those functions are executed when some event happens. And Michał will show you a very nice demo in a minute. It will be a very quick background session now, where we will have different events trigger function execution. So it uses JavaScript. JavaScript is becoming a very popular language. It started as a language for the front-end development, but now, thanks to Node.js, based on the Chrome virtual machine, we actually can also write the backend code in JavaScript very quickly. And thanks to that, you get very good performance of the Node.js and use the very big set of NPM modules. So Cloud Functions can be executed based on various events, as I said. So what are the examples of events that can trigger execution of a function? So there are so-called background events that trigger background functions. So background event is, for example, a file was created in cloud storage. So you can say, please execute this code whenever a file is created. And you don't have to write any code that observes your file system, etc. You can say, execute this function whenever a message arrives on PubSub. Or you can say, please execute this function whenever a request comes from a browser. Or a variant of that is a webhook. Webhook is a standard within, I think also becoming a pretty popular standard, to basically say, I want to modify a behavior of some application by registering a webhook that should be executed. A webhook is basically an HTTP endpoint. An HTTP endpoint that should be poked or should receive a request whenever some event happens. And we have support for webhooks in our Google applications that are visible here, but many other services externally also support webhooks. So an example. We have GitHub that Michał also used in his demo. GitHub is the most popular place to keep source code. All the open source projects, almost all of them, I think, are stored on GitHub these days, right? And in your open source project, you can, for example, on GitHub say, whenever a code is modified in my project, please send a packet to this webhook. And you can register a webhook that's running on Cloud Functions. And you can write very simple code that will be executed whenever someone modifies the code in your project. Or you can register a webhook for whenever someone talks to your phone, to your assistant, right? There is the assistant on Android, right? Right now you can talk to your phone or to the, how is it called? Google Home device. And you can register a function that's executed whenever someone talks to it. So, and also another example is Firebase. How many of you have heard about Firebase? Okay, 1/3, maybe half. So for those who haven't heard, Firebase is a platform for very rapid development of mobile applications or front-end applications, basically web applications. And it allows you to write the code that runs in a browser on the client, and you don't have to worry about the server at all. And the Firebase platform automatically manages your communication with the server, storing your data somewhere on some server. You don't have to care about it. But also, sometimes you might want to add, if you are using Firebase and you sometimes need to add some code that's executed on a server, then you can register, use Cloud Functions for that. Then they are called Firebase functions, but this is basically the same thing. And you can have some code executed on a server. So typically in a mobile app, it's best if most of the code is run on the client because it's the fastest. But there is some code that cannot run on the client. So for example, the code that does the credit card transaction. For a number of reasons, it should not run, it cannot run on the client. So then you can run this code as Cloud Function. A very simple example of HTTP function. This is all of the code that you have to write. 3 lines or 4 if you include the comment and the closing bracket. You just write a function that takes 2 parameters and just returns the result. That's all the code you write. Then you just go to the UI and say, this function should be executed when some event happens. So for example, when a request comes in. And you will see an example very soon. So now, going to the last demo of today.
Okay, before I discuss what the purpose of the demo is, let me just quickly deploy the function that will be part of this demo. So we have a function that involves sending an SMS. It's really the function. Actually, if we take a look at the code, is really short. This is the whole code. I don't know, like 30 lines or something, and that's actually the whole function. That function will run. It will take the input, and then it will transfer this input onto the service within Google, and then feedback the result to you. I will explain in a moment the whole flow. Just let me deploy this function because it takes a couple of seconds. So I have it ready. So I will just deploy this function to the web, so it will be available.
As Michał is doing that, notice one thing. You see only function here. You do not declare, I need a server, I need 5 servers, I need a server of this size. You just write a function that should be executed whenever an event happens. And we execute it whenever the event happens. We execute it on as many copies as needed. And you only pay for the executions. If the function is executed once, you actually the first, I forgot how many executions are free per month. I think some millions.
Yeah, something like that.
But then you just pay for number of function executions, and if needed, we'll use 1,000 servers to handle that. But if a function takes half a second, you just pay for half a second.
The main advantage is that you don't need to care about the server that runs the function, and you don't need to spend any time managing the operation system. You just execute that function whenever you need it. It's still deploying here at the bottom. We can again take a look at the specific place in the console which will show the cloud functions. Here we can see that the cloud function is still being deployed. The cloud function name is SMS. And now let me explain what this cloud function will actually do. So here I would like you to participate in this demo. We have the Polish mobile number, and I would like you to send a text message to this number. For the purpose of this demo, we need to communicate in English, and the text that you are going to text cannot be the one containing commas. But you can send the text specifying your feelings about today's event or about today's weather or the weather in general here in Poland. That message will actually be delivered via SMS gateway to the cloud function. That cloud function will be executed. That cloud function will send the text of the message that you are going to send to a special service within Google Cloud Platform. That service is natural language processing. So the service that actually understands the spoken language, or in this case, written language. It will analyze this text that you are sending, and it will use something that is called yeah, this is natural language, but the feeling. It will detect the emotions within the text, and it will tell you back by sending an SMS back to your phone how it understood what you sent. If this is a positive comment or the negative comment. So let's take a look if the function is already deployed. It seems like it is still being deployed. Something strange is actually happening with that function. So before it is deployed, we cannot really use it. So we have to take a look at what's going on. There is the error about not being able to see one of the modules, but I believe you can send the text now, and it should perform the operation. Yep, is it returning the results? Okay, so let's take a brief look at what we can see here. So if you are sending the text, and if it was in English and it didn't contain the commas, so hopefully you should get the response to this text message, and it shall say if your comment was positive or negative. And now what we can actually test is we can see those responses that you have sent. So for that I need to change the project to the one that the cloud function is actually running on, and I need to go to the Bigquery, so one of the services that we have been discussing. And with Bigquery, I need to log on to one other account, and we'll see the responses that were provided. Okay, so we have here the Bigquery interface, so another service from Google, and we can query the table that contains all the messages that are received from the participants. As you can see, there is a number of them. I hope you can find your own response here on the table. And next to the response, you can see the sentiment, so the perception that natural language processing service felt about the message that you have sent. The sentiment analysis is quite complicated. Basically, everything that is negative is the negative comment, and everything on plus is a positive comment. Basically, when you differentiate between the strong positive, so about 50%, and slight positive, which is below 50%. But this is how it works. It reads those comments. It determines the sentiment, performs the sentiment analysis on the message that you sent, and it sends back to you the response on the basis of this sentiment analysis. At the same time, it feeds this table with the results. So as you can see, this is one of the examples of the functions that can immediately execute and provide you with the results. And one other demo that I would like to perform for you is actually a demo that allows. Sorry, I just need to refresh. This one is the example where you perform another function. It's also very simple. That function works this way: that we have a bucket, which is the place where we can store any of the files. In this case, we will upload the file, and this is I will show you the file first because it's the one I have pulled today. So there's no special operation performed on this file. This is the file with some kind of message on it. It says "World's Finest" or "All Flash Quarterly." It doesn't really matter, but we will upload this file to the bucket on the service, and we have the trigger set on this bucket that whenever the file is added to this bucket, will actually perform an operation. And that operation will actually execute another service from Google, which is the Vision API. Vision API recognizes different objects in the photo. The cat image that Jarek was discussing before is the biggest example of the Vision API and the intelligence behind recognizing the cat on the photo. But in this case, we will actually use the cloud function to perform the detection of the text in this image. So here we have the cloud function that is called analyze image the text. And this time the result is given only in the log file, so you will not be able to see this result anywhere else. But as you can see, it's current date and time, and here is the result of the execution of this function. So it read the image first. You can see here the execution. Sorry, it skipped. So it read the image. It fed this image to the Cloud Vision API service, and then it executed this Vision API for the text detection, and it fed back the information about the text recognized in this picture. So you can see there is this World Finest All Flash Quarterly recognized from this picture. So this is another example of the cloud function and how we can use the cloud function to perform some operations on the external input. Thank you.
Thank you very much. So that was the last presentation. I think it concludes our the whole session. With this, you have seen in the example that Michał have shown that you can write very simple code that reacts to SMS. You don't have to write any integration with any SMS gateway, SMS provider. You just say this function is executed whenever SMS comes in, or this function is executed whenever file is created, and you don't have to look up what's the contents of the directory, whether it's different than it was a second ago when you checked it again. No, you just write a function, and this function executes when file changes. So that
I'm
makes
more than happy to share the code. If you are interested, just ask me after the event.
So as a result, this is the solution which you have to care about the least things. So thank you. Do you have any questions, comments? Yes?
Jarek.
I have a question about functions. Do we have access to all APIs like Datastore, Memcache?
Yes.
There, like in the Appengine or computer virtual machines?
So you have access to all the public APIs. I think there are some features in Appengine standard that are not accessible via public APIs, so those might not be. If there is a public RESTful API, you can access it from Cloud Functions.
Let me clarify, because I mean like Google services like Datastore and storage, Bigquery. I saw that you used Bigquery, right? So I mean those clients and APIs which you discussed so far, right? So
Those we can definitely. That's how this should work.
Thank
That's
you.
the microphone. Yeah. So those APIs you can definitely access. Yep. And by the way, I forgot to mention another cool thing. So the whole Cloud Functions product was built entirely out of Poland also, which I'm very proud of. My team built it last year, and we launched it in March. Also, a large part of Kubernetes is also built from Poland, but not all of it. So,
done.
Sorry?
well done.
Thank you. So I'm very proud. I haven't written a line of code in most of those projects, maybe in the first one, but yeah, I'm very proud to be working in such a place when actually core parts of the cloud platform are built in Poland, especially in the compute space. Another comments, questions, complaints, refunds? No refunds, sorry. Should have said it in the beginning. Okay, thank you very much. Thanks, Michał, for
before
all the help.
we actually conclude the session, I would like to invite you all to contact us if you need any help when you want to test your own applications or your own solutions in the Google Cloud. This is why we ask partners participate in that series of events. We are here for you to let you understand and enter the cloud more easily than on your own. So if you have any questions, I'm available here, and I'm more than happy to set up the meeting and discuss your needs separately.
Asha and Magda, a question in this context. Do you, so I understand correctly, everyone here signed up for the session, so can we send like follow-up contact email addresses to everyone here? So Michał, maybe you want to author this email and ask people to contact you with any questions. We can also send materials, links to the demos.
Yep.
Thank you.
Thank you very much.
Thank you.